Okay. So, very brief introduction to the samples. So, statistics studies populations, but usually uh, populations are very big and we need uh, a lot of people, big stuff, a lot of time and a lot of money to study them. And we can make sample and if we use samples, our study will be faster and cheaper. When we study some population, we are interested and we calculate these descriptive statistics, means, standard deviations, percentages, and so on. These descriptive statistics in entire populations, in entire population, are called parameters. But these parameters are unknown because we can't study the entire population, because this study will be or could be very expensive and very time consuming. But we study this sample and we can calculate the same descriptive statistics, means, percentages, standard deviations, and so on. These descriptive statistics in sample are called estimation. Estimations of parameters, or only estimations. But estimation is close to the parameter, but estimation is not exactly the same, is not exactly equal to the parameter. And the difference between parameter and estimation is called error. So when we work with samples, there always are errors. Our estimations are with errors. And this leads us to the next topic, to the topic of hypothesis testing, because when we test statistical hypotheses, we want to know whether the differences are within the errors, or the differences are larger than errors. In the first case, if the differences are less than the errors, then we say that these differences are not statistically significant, or that these differences are statistically insignificant. And in the second case, when the differences between estimations are larger than errors, then we say that these differences are statistically significant. And now we will start with hypotheses. I will start the presentation about the hypothesis. And first, we must define the hypothesis. We always define two hypotheses. The first one is so-called null hypothesis. And null hypothesis means that there is not a difference, or there is not an association, or there is not a relation between variables. The second hypothesis is so-called alternative hypothesis, and it means that there is a difference, or there is an association, or there is a relation between variables. Since we work with samples, we don't know which hypothesis is true. We know that one of them is true. Maybe H0 is true, maybe H1 is true, but we don't know. On the other hand, we gather data, calculate some numbers, and make decision. And our decision is that we accept H0 or H1. And you can see here that if the null hypothesis is true, and our data and our calculation lead us to the acceptance of null hypothesis, then we will make right decision. Our decision will be right. The same if the alternative hypothesis is true, and our data and our calculations lead us to the decision that we have to accept alternative hypothesis, then again, our decision will be right. But there are other two cases. If the null hypothesis is right, is true, but our data and our calculations lead us to the conclusion that the alternative hypothesis is right, this is error, and this is so-called type 1 error. In the opposite, if alternative hypothesis is true, but our data and our calculations lead us to the conclusion that null hypothesis is true, that we must accept null hypothesis, then we will make type 2 error. These errors, type 1 error and type 2 error, are also known as false positive conclusion or false positive decision, and false negative conclusion or false negative decision. So, why false positive? False positive because negative statement is true. A null hypothesis is negative because null hypothesis is that there is not a difference or an association. So null hypothesis is negative statement. Alternative hypothesis is positive statement. So the negative statement is true, but our conclusion is that we accept positive statement, and we have false positive conclusion or false positive decision. And in the second case, the positive statement is true, but our conclusion is that we must accept negative statement. So we have here false negative conclusion or false negative decision. And now I will ask you something. You know COVID-19, you know PCR test or antigen test. So imagine that one person goes to the hospital and performs PCR test. Can you say can you describe type 1 error and type 2 error? In this case, in the case of PCR test, what will be type 1 error and type 2 error?
Which are the variables? The test?
Yes, test. And one possible decision is that there is no COVID-19, that this person is not ill. This is null hypothesis. And the opposite, alternative hypothesis, is that this person has COVID-19. He or she is ill. So, type error or false positive and type 2 or false negative.
So the test will show that this person has no COVID, and this should be false positive because the negative is the true one.
I'm not sure. If the test shows that this person has no COVID, this will be false negative, because the true is that this person is ill, and the test shows that he or she is not ill. This is false negative. The true is COVID-19, sorry, but the test shows no COVID, and this is false negative. On the opposite, if the true is no COVID, but the test shows COVID, this is false positive.
Yeah.
Yeah. Okay. And my second question is comparing type 1 error and type 2 error, which is more dangerous?
Type 2.
Type 2 is, I think, is more dangerous.
Okay, why?
Because the person is ill, but the test shows that he's not.
Yes, and this person is
in danger.
Yes, of course, he or she is in danger, but he or she is dangerous for the others because could transmit this disease to them, because he or she will not know that he or she is ill. Yes?
Yeah, that's right.
Yes, okay. In the other case, if the person is not ill, but the test shows that he or she is, it's maybe it's also dangerous for him because this could produce to say fear, and he or she maybe will take some medicines which are not necessary, or which could cause additional effects. But here in this for this example, I also think that type 2 error is more dangerous for the population as a whole. So this example was important because when we test hypotheses, both types of errors are possible. And since both errors are possible, we want to minimize them. We want to minimize the probability of both errors. And a probability to accept alternative hypothesis when null hypothesis is true usually is denoted with Greek letter alpha, and in the opposite, probability to accept null hypothesis when this null hypothesis is true is 1 minus alpha. These two probabilities together are equal to 1 or to 100% if we present them in percent. For the type 2 error, we use Greek letter beta, and probability to accept null hypothesis when alternative hypothesis is true is beta. Then probability to accept alternative hypothesis when this alternative hypothesis is true is 1 minus beta, or 100% minus beta. So we want this alpha and this beta to be as smaller as possible. But unfortunately, these probabilities, alpha and beta, are opposite. If alpha decreases, then beta increases. And in opposite, if beta decreases, alpha increases. So we cannot minimize both probability. If we minimize one of them, we will increase other. And recommendation here is, since we cannot minimize both, then we could try to minimize more dangerous. So if type 1 error is more dangerous, then we must minimize alpha. Or if type 2 error is more dangerous, then we must minimize beta. And in this previous example, you said that type 2 error, beta, is more dangerous. So we could try to minimize beta. But I will continue with another example. So to prevent this COVID, we have vaccination. And these medicines are tested before their market authorization. And this test must answer two questions. The first question is this vaccine, this medicine effective? Do they cure this illness, this disease? And the second question is, are these medicines safe? So again, we have hypotheses. In the case of effectiveness, the null hypothesis is that this medicine is not effective. It doesn't cure this disease. And alternative hypothesis is that this medicine is effective. This medicine cures the disease. So again, please tell me define type 1 error and type 2 error, and tell me which of them is dangerous, is more dangerous.
Type 1 error is that vaccine is not dangerous for the health, will not affect negatively the health.
You speak about the safe. This is the next example. The first is about the effectiveness.
Okay.
Does this vaccine cure the COVID-19 or not?
If it would cure COVID-19 or not, the first positive will be that false negative will be that it cannot cure, but in fact it cures. This is one possible, and the false positive will be that it will cure and it cannot cure.
Okay, a little correction.
Okay.
The false negative is that test shows that this vaccine is not effective, but in fact it is. And the false positive is that the test shows that this vaccine is not, is effective, but in fact it is not. And my second question, which error is more dangerous?
Type 1.
Type 1. Why?
Because it test shows effectiveness and people got misled because it is actually not effective.
Okay. So, these two examples show that there is no strict rule. We cannot say that always type 1 error is more dangerous, or always type 2 error is more dangerous. In different cases, different errors are more dangerous. So in each hypothesis testing, we must decide. We must decide and choose one of them. If we make conclusion that type 1 error is more dangerous, then we must minimize alpha. And if we make conclusion that type 2 error is more dangerous, then we must minimize the type 2 error. Unfortunately, beta, the probability of type 2 error, is invisible in our research. This probability can be calculated, but usually this probability is not calculated. It's possible to be, but it is not. So we can see and can work only with alpha, only with probability for type 1 error. And this is warning to you. When we can see and can control only alpha, it will be dangerous. It can lead us to minimizing only of alpha. But I already said, when we minimize alpha, then we increase beta. But this increasing will be invisible, and we will not know how much. Maybe beta will increase a little bit. Maybe beta will increase with large amount. We will not know what we will not know how much the amount. We will not know the amount of this increasing. And after this more theoretical introduction, okay, I will skip this slide for now, and we will return to them later on, because I want to start with different hypotheses. There are some classical statistical hypotheses. Usually there are seven main statistical hypotheses, but in SPSS and in PSPP, we can perform only 4 of them. So I will show you only these 4 main hypotheses. The first hypothesis is about difference between two means. We compare two means. We compare means from two different populations. So our example will be to compare optimism between male and female. So we have a population of male, a population of female, and we want to compare their optimism. So I will choose analyze. After that, compare means. After that, independent sample t-test. Why independent? What does that mean? Means independent samples. Independent samples means that we have two samples and we form these two samples separately. First, we form one sample and then separately form another sample and then compare them. So, dependent sample, sex or gender is grouping variable. I will move sex to grouping variable and I must define groups. I must choose codes here, values of these groups. So 1 is male, 2 is female. I have to type here these codes, these numbers. And then optimism. Optimism must be moved from left to the right. And then, okay. And now, here is the result. First, here we can see mean optimism of males and mean optimism of females. And here we can see that for males, optimism, mean average optimism is 22.0. And for females, average optimism is 22.2. There is a difference. The difference is 0.2. But the main question here is this difference smaller or larger than the error? I already said that when we work with samples, always there are errors. So if this difference 0.2 is smaller than errors, then we will say that this difference is not statistically significant, and then we will accept null hypothesis. In the opposite, if this difference 0.2 is larger than error, then we will say that this difference is statistically significant, and then we will accept alternative hypothesis. To check this hypothesis, we must see the next table, independent samples test. But here, this table consists of two rows. In the first row, here you can see equivariance assumed. In the second row, equivariance not assumed. But we don't know which is true. Maybe two variances are equal, maybe two variances are not equal, but we don't know. To check this, we have to test another hypothesis about variances. Our main hypothesis is hypothesis about means. We compare means, but we have to choose first row or second row, and for this we need the additional hypothesis about variances. And here, these two columns, Levin test for equality of variances, these two rows are this test of equality of group variances. So how we make decision? To make decision, we use so-called significance level. Significance level in SPSS and in PSPP is denoted by SIC. Here you can see SIC. SIC is significance level. However, usually in publications, this SIC is not used. Usually, we denote this significance level with small letter p. P or p-value, this is symbol which we use for significance level. So when we calculate this significance level, the rule for acceptance of null or for acceptance of alternative hypothesis is here. I skipped it before. If significance level is larger than probability of type 1 error, then we accept null hypothesis. In the opposite, if significance level is smaller than probability for type 2 error, again for type 1 error, then we accept alternative hypothesis. And usually in social sciences, in psychology, in sociology, in public administration, and so on, we use 5% probability for type 1 error, 5% or 0.05. So here, significance level is 0.035. Since 0.035 is smaller than 0.05. So 3.5% is smaller than 5%. That means that we must accept alternative hypothesis. But alternative hypothesis means that two variances are not equal. Since they are not equal, that means that we can assume equivariances. So the right row is equivariances. Since the alternative hypothesis is true, that means that two variances are not equal. That means that we cannot assume equivariances. That the right row is here, equivariances not assumed. And then we choose second row. And after that, here from third to the last column, we have numbers in both rows, but we already choose the first row. And here is the significance level for the hypothesis of means. So this significance level is about equality of variances, and this significance level is about equality of means. But we must choose first row or second row, so we need this significance level first, and this significance level shows the row, the first or the second row. And here, this significant level, 0.66 or 66%, 66% is larger than 5%. So the final conclusion is that we must accept a null hypothesis. That means that the difference between males and females is not statistically significant. That means that this difference, 0.2, is smaller than sampling error. So this was the first hypothesis. Now I will show a chart. Unfortunately, this chart doesn't exist in PSPP, and I will show this chart in SPSS. This graphs, this chart is called error bar, and it looks like in this way. In this chart, these points here represent the means, mean of the males and mean of females. And these whiskers represent the error. So here you can see that the difference between means, the difference between these 2 points is smaller than the errors, because errors are here, they are too big, and the difference between means is here, and it is small. And since the difference between means, between estimations is smaller than errors, that means that this difference is not statistically significant. And this leads to the acceptance of null hypothesis. So this was one example comparing two means in two independent samples. But samples could be dependent or related or repeated. And in psychology, we have related or repeated samples when we test the same persons twice. Usually, we do this when we perform experimental research. Then we test group of persons, then treat them, and after that, we test the same group again. And we want to estimate the effect of treatment, whether this treatment has an effect or not. Since the persons are the same, since the group is the same, that means that we make sample only once. Only in the beginning, we have made this sample. After that, in the end, after the treatment, we use the same sample. We don't make new sample. And that means that two samples are related because, in fact, this is the one sample. The one sample tested twice. So I didn't find data in internet about related sample, about a repeated sample, about the same group before and after treatment, but I found data about acceptance and importance, and we can compare them. These data are in the next file. Yesterday, I sent 2 files. Today, we work with one. Now I will open the second file. So file open. The second file is staff survey. And here I will open and questionnaire of this survey, staff survey here. In this survey, sorry, I said acceptance, the correct is agreement. In this survey, we have 10 statements. And first, we ask individuals to say, they agree with these statements. From 1, not at all agree, to 5 agree with a very great extent. And after that, for the same statements, persons must estimate importance. Again, from 1 not at all important to 5 extremely important. Then 2 new variables are calculated. One variable about agreement and other variable about importance. And then we can compare agreement and importance. So I will choose analyze. Again, compare means, but now paired sample. Here there are different terms: related sample or repeated sample, paired sample. All these terms mean the same. So I will choose paired sample. And now I will make pair. So first I move agreement and then move importance, and you see here the first and the only one pair in our case is pair with agreement and importance. And this is enough. So I will choose OK. And let's see the result. And so first here we have average row score for agreement and for importance. And we can see that average score for agreement is 34.1 and average score for importance is 41.4. Again, there is difference. The difference is 7.3. And again, the question is this difference larger or smaller than sampling error? If this difference is smaller than sampling error, then this difference is statistically insignificant and we must accept null hypothesis. In the opposite, if this distance is larger than sampling error, then this difference is statistically significant and we must accept alternative hypothesis. And to answer that, we have again significance level. And significance level is 0. 0 is less than 5%. That means that we must accept alternative hypothesis. That means that this difference is statistically significant. This difference is larger than sampling error. And now, here in the presentation, the analysis in SPSS is almost the same as in PSPP. Again, we define a pair here, and this is conclusion. Significance level is less than 5%, then alternative hypothesis, then there is statistically significant difference between agreement and importance. And again, in PSPP, there are not graphs, but in SPSS, there is a graph, again error bar, and again points represent means, and whiskers represent errors. So in this case, you can see that difference between means, difference between estimations is larger than errors, because difference between estimations is big, and in the same time errors are small, and as a result the difference between means is larger than errors. That means that this difference is statistically significant. This means that we must accept alternative hypothesis. So we test 3 hypotheses until now. First, hypothesis about equality of means when the samples are independent. Second, test of hypothesis for equality of variances when the samples are also independent. And third, test about equality of means when the samples are related to repeated or paired. I said that I will show you 4 basic hypotheses. We already saw 3 of them. Now the fourth, the last hypothesis is the hypothesis about normality of distribution, about the comparison of empirical distribution with normal distribution. And here we use different approach, so-called non-parametric methods or non-parametric tests. And I will first of all, I will return to the initial file, to the first file for today's survey. Then we'll choose Analyze. Here we have non-parametric statistics, and then one sample, KS. KS, K and S are the first letters of names. K is Kolmogorov, S is Smirnov. So this is a test of Kolmogorov-Smirnov. This test is usually used when we compare empirical distribution with normal distribution. So I will choose this. After that, I have to find optimism and move to the right. Here, optimism, move to the right. And then I have to choose test distribution. Since the normal distribution is very important, as I said in the topic for measurements, when we create new measurement tool, new scale, one of features that we check is normality of distribution, and usually we use exactly the normal distribution. So I check here normal distribution, then press OK, and we have to move to the output. OK. Here is the result. One sample Kolmogorov-Smirnov test. And here in the bottom of the table is the significance level. Significance level is 0.012. That means 1.2%. 1% is smaller than 5%. That means that we must accept alternative hypothesis, and that means that empirical distribution and normal distribution are not the same. They are different. So we already compare these distributions. First here, yellow bars are empirical distribution, black line is normal distribution. Here we saw that maybe these two distributions are similar. Maybe not exactly the same, but close. After that, here we calculated percentages. Below the norm, 14.7%, in the norm, 67.8%, and above the norm, 17.5%, and compare these percentages with percentages of normal distributions, of normal distribution here. Compare with 16%, 68%, and 16%. And our conclusion was that they are similar. Not exactly the same, but similar. And now the Kolmogorov-Smirnov test shows that these two distributions are not the same. They are different distributions. So the correct conclusion is that our distribution is not normal. But when the distribution is not normal, this distribution could differ from normal distribution in two opposite directions. And here on the right, we have examples. If our distribution is not normal, it could be sharper or could be flat. Sharp or flat. And when the distribution is sharp, usually it is not a problem, because when the distribution is sharp, then more than 68% of population is between these borders. More than 68% is between mean minus 1 standard deviation and mean plus 1 standard deviation. But if the distribution is flat, then this is a serious problem, because then less than 68% is between mean minus 1 standard deviation and mean plus 1 standard deviation. And this is a problem because in social sciences, when we speak about norm, and when we use this word normal, this means normal compared to reference group. In social sciences, normal is not fixed, is not constant. In social sciences, norm depends on reference group. If a person is a part of a particular reference group, and if this person is similar to others members of this group, then this person is normal. And of course, if this person is different from other members of these groups or of this group, then this person is not normal. When we use this word normal or norm, we don't mean values. We don't say that norm is good, outside the norm is bad. Maybe in special cases, some special cases, maybe norm is something bad, but norm means that all members or majority of members of this reference group are similar between them, and if one member is similar with others, he or she is in the norm. If one member is different from others, then he or she is outside the norm. For example, I could say to, 1 century ago in the Polynesia, it was normal to eat people. Cannibalism was norm because majority of members of these communities were cannibals. But our values is that cannibalism is not good. This is not good thing, but it is norm. Norm means that all of them or majority of them are cannibals. Whether this is good or bad doesn't matter in the case. So in social sciences, when we define norms and when we calculate the borders of the norm, we need majority. We need a big part, large part of this reference group to be between these borders. And if 68% or more of 68% of persons are between these borders, that means that we have norm. We could say that norm is this. between mean minus 1 standard deviation and mean plus 1 standard deviation. But if the percentage here is less than 68%, that means that this majority is not so big, and this makes norm somehow problematic. So if the distribution is not normal, but if the distribution is sharp, that means that more than 68% are between mean minus 1 standard deviation and mean plus 1 standard deviation. That means that we have enough persons in this interval between these borders. That means that we have norm, sure. But if the distribution is not normal, but it is flat, that means that between mean minus 1 standard deviation and mean plus 1 standard deviation, the percentage is less than 68%, and that means that not so many persons are there between these borders, and that makes norm somehow problematic. So in our case, we found that the distribution is not normal, but we also found that between mean minus 1 standard deviation and mean plus 1 standard deviation, in this interval between these borders, there are 67.8%, almost approximately 68%, which is the same as this theoretically expected value. So we could see, okay, our distribution is not normal, but it is not a problem because the percent of person in the norm is big enough to use this norm, to be sure that majority of this population is between these borders. So I will continue with the presentation because here again in PSPP, unfortunately, there are not graphs, but in SPSS there are two different graphs according to visualization of comparison between distributions, and these two graphs are PP plot and QQ plot. So this is a PP plot. Here we have this line here, this straight line. This line represents normal distribution, and these points here, they represent the empirical distribution. And if these points are on the line or close to the line, then we could say that these two distributions are identical or are very close. In our case, some of these points are on the line, some of them are very close to the line, so we can say that these two distributions are very close, our empirical distribution and normal distribution. QQ plot is similar. Again, we have straight line. This straight line represents normal distribution, and points. These points represent empirical distribution. And again, the rule is the same. If the points are on the line or close to the line, then two distributions are identical or close. And if these points are far from the line, then these distributions are different. And if we compare these graphs and these graphs, we could see that QQ plot shows that in the middle, these two distributions are very close, but in the right and in the left, they are different. PP plot shows that both distributions are close. There is no difference. There are not points far from the line. And when we compare these two graphs with our first graph here, we could see that maybe QQ plot is more accurate, because QQ plot shows that in the middle distributions are almost the same, but the difference in the right, and there are bigger differences in the left. Here is QQ. Small differences in the right and bigger differences in the left. And comparing to this chart, here we can see the same small differences in the right and bigger differences in the left. So I think this is all done. Okay, this is all for this topic about the hypothesis testings. Questions?
No, thanks.
Okay, so this topic about hypothesis testing is important because next 4 topics are about analysis of associations or analysis of relations between variables. We will start to analyze factors, results, independent variables, so on. But always the first question is there a relation? And if the answer is yes, this is alternative hypothesis. There is a relation between some variables. If answer is no, this is null hypothesis. There is not a relation between some variables. And since we work with samples, that means that we always have sampling errors. To answer these questions, is there relation is not, whether there is or there is not relation between variables, our first step is to test hypotheses. Of course, these hypotheses are different. These hypotheses are tested with different methods, but they are hypotheses, and it's very important to understand the principles of hypothesis testing before analysis of relations. Okay. Stop recording.